Okay, today we're going to be continuing on with some probability, but the problems are going to get more complicated. You can see our learning targets. We're going to use combinations to find the probability of an event. Also, we're going to learn how to use circular permutations to count the number of ordered arrangements without replacement in a circular setting. Take a look at number 1 with me. You've dealt with a problem where you had to select a number of items, but now it's going to get more complicated. It says from a set of 5 black balls and 3 white balls, you can say that 4 balls are going to be selected at random without replacement. Find the probability of drawing 2 black and 2 white balls. Now, you see, in the past, when you looked at homework, you would be asked the very simple question, hey, what's the probability of drawing a black ball or the other ball? And it wouldn't be all that challenging. Right now, you can see that there are more black balls than the white, meaning that they're not equally likely. Yet we'd like to find the probability, if we were to just select 4, that we would actually arrive with 2 black and 2 white. Now, of course, probability is still going to be known as the number of successes divided by the possibilities, or the possible. So, look, if I were to look just about how to find how many possible arrangements I could make, of course, there are black balls, there are white balls. How many balls together, all in all? 8. Now you're going to select 4, but order won't matter. When you're, making this arrangement, and by the way, you get this in poker hands too. You're going to see this in the game of poker. We might even talk about some poker hands in particular in just a moment. Where you might get the queen of hearts and a 7 of clubs and so forth, and you won't care which one came first. In the end, you have the same collection of items. That's what we're seeing here. Combinations come to our rescue. How many balls did we have total? 8. We'd like to select 4 of them. So right now, there's no distinction in color. It's just, look, you've got 8 items total. You want to select 4 of them. Now, we'll use a combination to work that out in just a moment. But up on top, guys, you're going to say, well, wait a minute. You've got the situation where you need to select 2 of the black color. So how many black balls do we have total? We've got 5. And I'd like to say 5, choose 2. I'm going to say how many different ways could we select 2 of the black ones out of a total of 5? Whether they're distinguishable or not, this is what you have. But that's not the end of the story. You're going to say, now in addition to that, that would be the number of ways I could select 5 black balls. I also want to get 2 white ones from a collection of 3. So I'm going to say out of 3, choose 2. The fundamental counting principle is being used right here. And by the way, you do this a lot in card games as well. Well, right now, I hope you can see that the rest of the problem is just mechanical. It's just a matter of saying, could you work through these numbers and get a direct answer? Of course you could, and that's not the hard part at all. Sometimes kids ask, is it okay to rely quite a bit on the calculator here? And the answer is, of course, yes, you certainly can. You could say, what would I get with 5, choose 2? Well, within a second, you'd get an answer of 10. What about 3, choose 2? Well, how about we just go second enter, and we just type over that, and we get 3. You'd say, well, what about down below with the 8, choose 4? Second enter will allow us to just retype over these fast. And you can certainly do this. Evidently, that's 70 down below. Right now, I hope you can see that the zeros could cancel out. And you'd be left with 3 times 1 is just a 3 all over 7. So we'd have a 3/7 probability of this happening. Okay, is this making sense so far? Let's take a look at a very similar problem. By the way, you're going to get some of these on your worksheets. You look at these next problems, like number 2, and you might have the famous sock problem where it says, look, you've got, in a drawer, 5 white socks, 3 red socks. Let's say that you reach in there without looking, or it's the middle of the night, you pick out 2. What's the probability that the socks match? Now, this is a tougher problem. It's a little bit more challenging because if you think about it, matching can happen in one of 2 ways, couldn't it? You could get 2 that are white in this problem. You've got 5 white. Or you could get 2 that are red. And this is where we're beginning to get more involved. You can say, well, case 1, you want to get 2 white socks. Case 2 is going to say, well, look, there's also this other situation. You could have a match if you had 2 red socks as well. And we have to consider these cases separately. So here we go again, very similar to the problem that we were just doing, if you really think about it. How many socks do we have total? 8. And we're going to say, well, look, out of possibilities, I'm going to say out of 8 socks, select 2. But now if you're really thinking about it, for the numerator to get a success, you're going to say, well, I want to make sure now I'm going to take 2 white socks. Okay, and order doesn't matter whether one comes out first and the other one even has a little tear in it or something. You wouldn't care, which one comes first or second. It's the same pairing for you. So you'd say, well, look, out of 5 items, select 2. Look, here we go again. We could let the calculator help us out so much. You could say, well, look, down below it's going to be 8 choose 2. That's going to be 28. 5 choose 2, well, that's not going to be that much different. All you got to do is just go all the way over here. You can see you get 10. And you could reduce this, 10 over 28, we could divide out a 2. You'd get 5 over 14. That, by the way, is not the final answer. It's just the probability getting a white matching pair of socks. Well, the red is so incredibly similar if you really think about it. You'd say, well, I still have 8 choose 2, and I already know that 8 choose 2 is 28. But now I want to select 2 red socks. So up above, what will I have up there? 3 out of 3 red socks, choose 2 of them. And it won't take you too long to realize that 3 choose 2 is one of the more famous combinations you could get. It's just the number 3. You'd say, well, that's 3 28s. You won't even be able to simplify that. Well, now for the big question. We've got our 2 different cases. What's the probability that our socks match? What do you think we have to do? Take these 2 numbers and add them together. Sometimes kids would be like, I don't get why you're adding them together. Listen, we did homework just a minute ago. Didn't we see that if you had the probability of A or B, it was the probability of A plus the probability of B minus the probability of both of them occurring? Could you get in one of these situations that both of them are occurring? You'd be like, hey, look at this. I've got a white pair of socks and a red pair of socks. Well, no. Those are mutually exclusive cases. Either you're going to get 2 white socks or you're going to get 2 red socks. You're not allowed to end up with 4 socks at the end. You're only going to select 2. So add your cases together and then you're in good shape. We doing okay? Guys, one more little problem here. Circular permutations. Given that you've got n objects around a circle, There are so many ordered arrangements. Let me give you the formula real quickly. It's n minus 1 factorial. There will be n minus 1 factorial ordered arrangements. Now, we have to talk about what's going on here. If you're sitting people around a circle, I guess what I want to point out to you is where a person is sitting really doesn't matter as much. Like you could have person A, person B, and so forth. Person A could be slid anywhere around the circle. It's not the seat location that matters the most. What matters the most is who is on your right, who is on your left. So I could turn that circle around, and I guess what I really want to point out to you is if I gave you here, we've got A, B, and here's C, D, and E. This second picture that I just drew would be exactly the same setup as what we had before. What would make a difference is if person A now had person C on their left side, on their left hand, and so forth. So that is first and foremost so important. We don't care about, relative locations. Rather, we care who's on your right side and left side. Sometimes kids will say, well, okay, I guess I see that, but where on earth is this n factorial coming from? That just seems to be crazy. Why not n factorial itself? Let me give you a little quick quasi-proof, if I may. Let's just say that you've got n people sitting around a table, okay? And right now, you have one of them have a seat anywhere. Somebody's going to have to sit down first. And by the way, it doesn't matter where they sit down. But right now, you could say, let's see who's sitting on their right-hand side. If I've got n people, how many people could I choose to sit on their right-hand side? N minus 1. And then you could keep going. How many people could I choose from for right here? N minus 2, then N minus 3, and so on. And you keep going around until you're down to one person. That one person would be the person on the left, the person 1. It's N minus 1 factorial. That's the proof why that works. That being said, some of these problems then become quite simple. Given 5 people are seated around a circle. By the way, that's the original picture that I drew. A, B, C, D, E. How many different arrangements are possible? Well, that becomes rather routine. If you'd say n equals 5, the answer is 4 factorial. And 4 factorial is just 4 times 3 times 2 times 1. So that's 24, guys. And we are done. And we are done, okay? So what I'd like to do is to get you the worksheet.